Multivariable Calculus, Section 13.8, Surface Area. The main idea starts with the mapping of a two-dimensional surface onto a three-dimensional surface. So on the right you have a flat region in a UV plane, R, and each point in that U, V gets mapped into three-dimensional space onto a point X, Y, Z. Now the way we do that mapping is we map onto a vector function. So there's that red position vector, and we find that vector by a recipe of three functions, each of which is a function of two variables. And so you have a function x, a function y, and a function z of the two original variables u and v that map onto the three-dimensional surface. R of uv is defined on a region R, the domain, in the uv plane, and has a range consisting of vectors that determine a set of points on a surface S in 3 space. Now, in order to keep this a nice surface, this surface S defined by R is smooth if the partial derivatives R sub u and R sub v are continuous, non-zero, and non-parallel at each interior point of R. If the three functions are continuous and the partial derivatives are continuous, then that means there aren't going to be any holes or gaps, and also you need the non-zero and non-parallel as well as the continuous derivatives in order to not have sharp corners or cusps that would cause a difficulty in setting up an integral. So the idea here now, moving on, is going to be to approximate our surface area in 3D with little flat parallelograms. And we're assuming we have constructed our three-dimensional surface from a flat two-dimensional surface. Then what we do is we move from those approximate parallelograms, shrink them down into instantaneously small parallelograms, and then use an integral to compute the exact surface area. So here's a picture of what we're talking about. We have our vector r, which is x, y, and z of two variables u and v, which are on the flat surface. And if we compute the partial derivatives r v sub I and r u sub I, they will create a parallelogram tangent to the surface area. And those partial derivatives are as follows. The partial derivative of r with respect to u can be written in either Newtonian or Leibniz notation. And then for r sub u, you treat v as a constant, and for r sub v, we treat u as a constant. Now, what's the area of that parallelogram? Well, it's the length of the cross product, which is illustrated. The cross product is the normal to the surface and to the parallelogram. And so the area is the length of the normal, or which is equivalent to the length of the cross product of r sub u and r sub v at each particular point. And so each particular point has a subscript. So then what we're going to do is, instead of actually sitting down and doing a whole bunch of parallelograms, we're going to let that change into instantaneous lengths, which will be instantaneous areas at each point. And so instead of doing approximations, we'll do the integral over the region uv that's defined by u and v, and do the instantaneous areas, which are the lengths of the cross products, and then integrate with respect to u and v over that original flat area defined by the u and v axes. Now, in actuality, most of the time we're going to use x and y for u and v, and so that the region is going to be directly underneath the surface shown on the xy plane. But we can also use r and theta to do some, if it's more convenient, and technically any two variables at all, but we're going to only mainly look at using x and y, and then a little bit at r and theta for u and v. Now let's look at surface area in rectangular coordinates, and what we're going to do here is just let u equal x and v equal y. So we're mapping from one xy plane into xyz space. Then r becomes just xi, yj, and f of x, y, k where f of xy is your z value. So you could just use a z there, but I wanted to make it clear that f is a function of x and y. And so then our partial derivative with respect to u is the partial derivative with respect to x. So the derivative of x is 1. Derivative of y is treated as a constant, so that's 0. And then the derivative of the f function is the partial derivative of f with respect to x, or z sub x if you prefer. And then our v is the same thing, except we use y for v. And so the partial derivative of x is 0 with respect to y, and the partial derivative of y is 1. And then we have the partial derivative of our f function with respect to y, or z sub y if you prefer. So now we need the cross product because we're going to want to integrate the length of the cross product. And we determine that with a determinant. And the quick way of doing a 3 by 3 determinant is to copy the first two columns and then multiply up the diagonals and then down the diagonals. And then we take the bottom minus the top, and that gives us negative f sub xi, negative f sub yj, and 1k. So we're going to need to integrate the length of this cross product, which would be the instantaneous areas of all the little tiny parallelograms. So our original integral has an x and a y instead of a u and a v, and our iterated integral goes from the x limits and the y limits of the square root of each of those components of the cross product squared. So now let's look at surface area in cylindrical coordinates. This time we're going to change from x, y, and f of xy to r and theta. And so x becomes r cosine theta, y becomes r sine theta, and our function, it'll be a different function, acts on r and theta. So we're going to take a region in the r theta plane and map it into 3 space. Notice that u is r and v is theta, and z then is your function of r and theta. R sub u is r sub r, and if we take those partial derivatives individually, we treat r as the variable, and so cosine theta is just a constant times r, and then sine theta is a constant times r, and then the last one will be g sub r, or in Leibniz notation we have this symbol. And then r sub v is r sub theta, and so theta is the variable and r is considered as a constant, so we get the derivative of cosine theta is negative sine theta, keep the r. Derivative of sine theta is cosine theta, keep the r. And then again the derivative of z with respect to theta. And you can use a z sub theta there, or you can use a g sub theta, whatever notation you like best. So now we want to cross those two vectors, r sub r and r sub theta. Here's our determinant, and we would repeat the last two columns and multiply up and down the diagonals and get a big mess. So you can work that out on your own if you wish, but it simplifies to the following. The partial derivative of z with respect to theta times sine theta minus r times the partial derivative of z with respect to r cosine theta for the first component. And the second component is the opposite of the partial derivative of z with respect to theta cosine theta minus r times the partial derivative of z with respect to r sine theta. And then the third component comes out to just r. So now we need the length of this cross product for our integral. And that's another bloody mess, which you can work out on your own if you wish, but it simplifies with the magic of trigonometric identities. We get simplification, the square root of r squared plus the quantity r, partial derivative of z with respect to r, that quantity squared, plus partial derivative of z with respect to theta squared. And so our integral then has r and theta instead of u and v, and the limits of integration reflect our r and theta variables, and then we have the square root of what we had above with respect to r and with respect to theta as our surface area integral. Okay, at this point I want to do a little bit of clarification. Here's our generic integral for computing surface area with generic parameters u and v. And we've looked at using x and y as these two parameters, and we've looked at using r and theta as our two parameters. Well, now here's where the confusion came in last year for a few students. When we used r and theta, here's what we got, right? Here was our answer. Now, here's what confused some people, and I want to clarify this. There's no r there. Remember when we used to change from rectangular coordinates to polar coordinates, the polar rectangle involved setting dA, which was equal to dx dy, equal to r dr d theta. But you'll notice there's no r there. There's no r here, because the difference here is that we're using r and theta from the get-go as parameters. We're not changing from one set of variables to another set of variables, and therefore there is no r there. We are using r and theta as our parameters, not changing from rectangular coordinates to polar coordinates. Hence, no extra r. Okay? So here's a picture of what we used back when we were doing areas and volumes using a polar rectangle. It's called a polar rectangle. It's not a real rectangle because it doesn't have parallel sides and two of the sides are curved. But when we computed the change in area for that shape there, we got r change in r times change in r times change in theta for the area, and that's where that extra r came from. But for these problems in this lesson, for surface area, we're not using a polar rectangle for area. We're using a parallelogram for area. And when we use r and theta as our parameters, the two vectors that define that parallelogram are r sub r and r sub theta. And so to get the area of the parallelogram, we use the cross product and then take the length of the cross product. So we're using a parallelogram, not a polar rectangle, and I just wanted to clarify that since there was some confusion last year. Okay, so now we're going to go and take a look at some of the exercises. Number 2, find the area of the region in the plane z equal 1 plus 2x plus 2y that lies directly above the region in the xy plane bounded by the parabolas y equal x squared and x equal y squared. So here's the region in the xy plane, that's the domain, and here's my three-dimensional rendition. Notice that to get the three-dimensional picture, what I did was I figured out that the image of 0, 0, 0, when I plug 0 in for x and 0 in for y into the plane, z equals 1 plus 2x plus 2y, I get 1 for my z coordinates. So there's the image of the origin. And then when I plug 1, 1, 0, well, just 1 and 1 for x and y, into the plane z equals 1 plus 2x plus 2y, I get 5 for z. So the image of the other point on the other end of this petal shape is up there at 1, 1, 5. So here's my handy-dandy integral formula for surface area. And I'm going to integrate with respect to y first. You could do it either way, but I'm going to use the fact that it's vertically simple to set up my integral. You could do it the other way too, if you wished. So I'm going to integrate with respect to y first. So the inside limits in the iterated integral are from x squared up to the square root of x. That's how y moves. And then x is going to move from 0 to 1. Now, meanwhile, my partial derivatives of the z function, the partial derivative with respect to x is the coefficient of x, which is 2, and then the partial derivative with respect to y is the coefficient of y, which is also 2. So that square root comes out nicely to the square root of 9. So we're going to integrate 3 with respect to y, and we get 3y evaluated from x squared to root x. So that gives us an integrand of 3 root x minus 3x squared, which is easily integratable in terms of x. So we get 2x to the 3 halves minus x cubed, evaluated from 0 to 1. And when you plug the 1 in, you get 2 minus 1. And when you plug the 0 in, you get 0. And so the area of that blue tilted section that's on the plane, z equals 1 plus 2x plus 2y, is 1 unit, or 1 square unit. Number 4, find the area of the part of the surface 2z equals x squared that lies directly above the region inside the triangle on the xy plane with vertices 0, 0, 1, 0, and 1, 1. So here's the triangle, And notice that y goes from the x-axis up to that line, and then x can go from 0 to 1. And what's the equation of that line? Well, pretty obviously y equals x. And then for the three-dimensional surface that we're talking about, I just computed the z values at those three corners. So 0, 0, 0 stays at 0, 0, 0. And 1, 1, well, let's see. When x is 1, then z is going to be a half. So we get 1, 1, half. And then at 1, 0, again, z is going to be a half. So the little blue surface is my curved surface that's part of the 2z equal x squared surface. Here's our integral in terms of x and y. And notice that z, if we solve for z, we get a half x squared, because I'm going to need fx and fy, and that's your function that we're taking the partial derivatives of. So again, I'm going to switch and integrate with respect to y first. And so y is going to go from 0 to x, and then x is going to go from 0 to 1. And then in my integrand, the partial derivative with respect to x of z equals a half x squared is 2 times a half x, so that comes out to x. So we have x squared. And then the partial derivative with respect to y is 0, because there is no y in the formula for z, for my function z. So then we integrate with respect to y, and that means we treat the square root of 1 plus x squared as though it were a constant. And then we evaluate that from 0 to x. So y goes from 0 to x. And we end up with x times the square root of 1 plus x squared. And we can integrate that with respect to x using simple u sub in our heads probably. And we get 1/3 1 plus x squared to the 3 halves evaluated from 0 to 1, which comes out to 1/3 the quantity 2 root 2 minus 1. Now if you approximate, that's about 0.6. And that kind of makes sense because the area of the pink triangle is 1/2, and that blue curved surface should be a little bit bigger but not much. So about 0.6 makes a lot of sense. Number 10. Find the area cut from the surface z equals x squared minus y squared by the cylinder x squared plus y squared equals 4. So if we take a look at the xy plane, the image of the cylinder is a circle, and so that's going to come out towards you along the z-axis. And what we're going to do is, let's just do the first quadrant and then multiply our surface by 4, because we have symmetry here amongst all 4 quadrants. So we're going to just do the surface above and below the first quadrant on the xy plane, and then multiply our answer by 4. Now our region then in that first quadrant is vertically simple, so we will integrate with respect to y first, and y is going to go from 0 up to the curve square root of 4 minus x squared. Now notice that if z is 0, so down on the xy plane, y is plus or minus x, and so our pink region there is going to be cut through, the surface is going to cut through in a straight line from the origin on out. So that's going to help me draw my three-dimensional picture. See, on the xy plane I've got the pink region in the first quadrant, and then the surface that we're interested in cuts through there along that line that goes from 0, 0, 0 to root 2, root 2, 0. And then also if you plug in 2, 0, which would be one of the points at the corners of that pink region, you get 4 for z, because it's 2 squared minus 0 squared. And that also helped me draw it. Notice that if y is 0, then the image on the xz plane is the parabola z equal x squared. And if x is 0, then the image on the yz plane is z equal negative y squared. Now I guess we could have used symmetry and just done the first octant multiplied by 8, but it doesn't matter because surface area will always come out positive because of the square root, the positive square root we use in the formula. So here's our formula again, and our integral. And again, I'm going to switch and integrate with respect to y first, because y is going to go from 0 up to the curve square root of 4 minus x squared. So my iterated integral, and don't forget we have to multiply by 4, x is going to go from 0 to 2, y is going to go from 0 to the square root of 4 minus x squared. And then looking up at our surface, our function, z equals x squared minus y squared, the partial derivative with respect to x is 2x, and the partial derivative with respect to y is negative 2y. So that's what we put in the formula for the integrand. Now, this integrand cannot be integrated, or at least not easily, with respect to x and y. However, if you'll notice, if you simplify what's under the radical, you get 4 times the quantity x squared plus y squared, which is reminiscent of polar coordinates, because x squared plus y squared equals r squared. So we're going to change this integral to polar form. Now that gives us 1 plus 4r squared under the radical. And if you look at the original region, you'll notice that r is varying from 0 to 2, and that if we're just using that first quadrant, theta is going to vary from 0 to pi over 2. Now we have to change our dy dx to polar form, which you will recall gives you an extra r. So dy dx becomes r dr d theta. And now we can integrate using simple u substitution. And we get 4 times integral from 0 to pi over 2, 1/12 the quantity 1 plus 4r squared to the 3 halves. And that's evaluated from 0 to 2. Now the 1/12 can come out, and the 4/12 is 1/3, and if we throw 2 into our antiderivative, we get 17 root 17, and when we put the 0 in, we get 1. And now when we integrate with respect to theta, it's just that constant times theta evaluated from pi over 2, from 0 to pi over 2 rather. And so our final answer is pi over 6 times the quantity 17 root 17 minus 1. Number 14, find the surface area of the sphere r squared plus z squared equals a squared that lies within the cylinder r equal a sine theta. This is in terms of r and theta. I guess we'll use r and theta as our parameters. What do you say? Now, you know me, I like to have a picture of what I'm doing first. Makes me feel better and helps me set everything up. So first I'm going to look at the sphere. When z is 0, we get r equaling a or negative a, right? And then if z is a, r would have to be 0, and if z is negative a, r would have to be 0. So that gives me an idea of what the sphere looks like. And then what's with the cylinder? Well, let's take a look at a flat picture of r equal a sine theta, which I found online. And so the cylinder then would just, that would be on the xy plane, and then the cylinder would come up towards you along the z-axis. So here's my picture. It took me a while to draw, but that's what it looks like. And so what we've got here is the surface area of the sphere that lies within the cylinder are those two little tiny areas at the top and bottom of the sphere that are kind of tilted. Okay, so that's what we're finding the surface area of. So there's 2 of them. We gotta keep that in mind. So here's our generic integral when using r and theta as our parameters. We could redo the whole thing, but let's not. Let's just use what the text and this video has already done. So we're going to use do the surface area of the sphere. So that's what we're going to use for our derivatives. And so if we solve for z, we can take our derivative with respect to r and our derivative with respect to theta. But notice that this is only the top half, the top portion, the top little piece, because we're assuming z is positive, but z could be plus or minus the square root of a squared minus r squared. And so there's another identical surface down there at the bottom. So if we take the derivative with respect to r, we get this. I didn't show the work, but you can do that. And what about theta? Well, there is no theta, so z theta is 0. So here's our integral filled in. Notice there's a 2 in the front because we have 2 of these little tiny surfaces, one at the top of the sphere and one at the bottom. And notice that the theta only goes from 0 to pi because we get the entire circle a sine theta when we let theta go from 0 to pi, not 0 to 2 pi. And then, of course, r goes from the origin out to the circle defined by a sine theta. So those are your limits. And then we've got r squared plus r times zr, that quantity squared, plus 0 squared. So there it is, cleaned up a little bit, and also taking that r squared and multiplying by the common denominator of a squared minus r squared so that we can combine everything under the square root. So moving on with our algebra, here's what we have so far. Multiplying out the r squared times the numerator a squared minus r squared, we get that, and then notice that the r to the fourths cancel. Isn't that convenient? And so now we're left with, in our integrand, ar out of the square root, and then the square root of the denominator a squared minus r squared. Now we're getting somewhere. I can do, to integrate this by hand, I can do a simple u sub. I have to, I mean, you can't put it in your calculator, well, unless you've got a special calculator that does two variables. Let u equal a squared minus r squared, and then du is negative 2r dr. Okay, so that looks good. So then we need a negative 1/2 a, and then we're substituting for all the other stuff, and that becomes u to the negative 1/2. Now notice our limits have to change, right? So when r is 0, u is a squared minus 0, which is a squared, and when, unfortunately, when r is a sine theta, u is going to be a minus a squared minus a squared sine squared theta. But don't despair, because we can use an identity on that. That becomes a squared cosine squared. Okay, so now the antiderivative of u to the negative 1/2 is 2u to the positive 1/2. And so the 2 and the 1/2 cancel, but we still got a 2 on the outside. And so now we have, bring the negative out and bring the a out, and we get negative 2a with our integral from 0 to pi u to the 1/2, and from a squared to a squared cosine squared. Now here's where I almost made a mistake. When you plug a cosine theta in to u and take the square root, you think it's going to be a cosine theta, don't you? But technically it should be the absolute value of cosine theta. And we got a slight problem here, because cosine is going to be negative for half of this integral. From pi over 2 to pi, it's going to be negative, and we don't really want to put absolute value there, because how are you going to integrate that? You know, that would be tough. So instead, to take care of that little problem, we'll just double it from 0 to pi over 2 so that the negative and positives don't cancel out. So now we've got, we bring the a out also and switch it around to get rid of the negative. So now I've got 4a times the a I took out, 4a squared, and then switched around 1 minus cosine theta from 0 to pi over 2. And I'm running out of space again, so let's move on to another slide. Here's what we've got. Easy to integrate. 1 becomes theta, cosine becomes sine theta, and we're going to plug in pi over 2 and 0, and here's what we get, which simplifies to 4a squared times the quantity pi over 2 minus 1. Phew! That was quite an ordeal. Okay, now I'm going to leave you with a picture of surface areas that are changing. So you could think of these as four-dimensional surface areas changing with time, where time is the fourth dimension. Doo -doo 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 -doo.